Hello. So up to now we've talked about motion in rotating frame, and when we talked about rigid body, what we did was we attached a rotating frame, or we attached the frame to a rotating rigid body, a body which had pure rotation. Now I briefly mentioned that if you have a translation and rotation, or on top of rotation, then all we need to do is to add the translational component to our rotational component. So what happens here is that let's say we have a rolling disc. Then if you look at this rolling disc, and let's look at this reference line on this rolling disc, you can decompose the motion of this rolling disc to a translation as if this line stays as straight as it was before, and then a rotation about this point, right? And then you can have the total motion, or the actual motion of the rolling disc. In general, what you can do is, let's say I have this body, and this body's final configuration looks like this. Ignore my drawing issues, but so we can always decompose the motion, this planar motion, to a translation. When we have a translation, we said that all points on the body translate on parallel trajectories. So in this case, we have these two straight vectors describing the position as if the body was only translating, and then a rotation about this point takes the body into its final configuration. So we have a translation A1 B1 to A2 B1 prime, and a rotation A2 to B2. Again, ignore my drawing issues. So in general, so if I have a body, this is my body, and then this body moves at an arbitrary instant of time. I'd like to analyze the motion of this body. So what I'm going to say is, all right, so this body can translate along these lines. So let's say the body translates, and the point A, which was initially here, now it's here. So, and then I'm attaching a frame to this rigid body, and my initial I hat and J hat, now it's I prime and J prime are body attached frame, but they are parallel to I hat and J hat. And then at this point, I'm going to say that this body now rotates about this point A. So if the body rotates, the body attached frame also rotates. And I prime and J prime are taken to I hat and I double prime, I hat double prime, and J hat double prime. All right. So if I were to describe the motion of these points, the arbitrary motion of these points, RB is our position of these points. RB is RA plus RB plus, with respect to A, right? And if I differentiate this, because now what I'm interested at the end, what we are interested in is velocity and acceleration of this rigid body. So I'm going to differentiate both sides. I get R dot B equal R dot A plus R dot B with respect to A. Now, R dot A, we said that the body translates initially about this, and then at this instant of time rotates about A. So the motion of A can be described by its translational vector, right? Because at its final point, the body rotates about A. And when the body rotates about A, we go back to the problem we had a couple lectures ago rotation or acceleration and velocity in rotating frame, in body attached rotating frame. It's exact same problem. And for that, R dot B with respect to A is going to be equal to omega, which describes the rotation or the angular velocity of rigid body in angular velocity of rigid body, and cross RB with respect to A. Right? So if you go back to your lecture, the only thing you need to do is to replace your R with RB with respect to A, and you get this component which is only due to rotation about A. So the first component is only due to translation, and the second component is only due to rotation. Now, what we can do is we can differentiate this equation again and compute acceleration. So what we're going to do is we're going to get RA double dot, okay, plus omega dot cross R B with respect to A plus omega cross R dot B with respect to A. And what is that? It is omega cross RB. So this is equal to B with respect to A plus omega cross R B with respect to A. Now pay close attention here. You already knew this. So you could have directly say, all right, I know what my acceleration components are going to be in my rotating frame. If we had only pure rotation about A, these are going to be our tangential, again, and centripetal component of acceleration when the body rotates about point A. So you only, as I said, you needed to add the translational component to these two components to get the total acceleration of rigid body. Pay very close attention here. This is a cross product, and this bracket matters, meaning that, so you cannot say I'm going to cross product omega with omega and then cross product with RB with respect to A. Right? The order of this cross product matters. So if you think about it, you can even think about it as your right hand rule. So let's say I have two vectors, A and B, two arbitrary vectors. I'm just explaining this there. A cross B is not the same as B cross A, because the result does not point in the same direction. So it's a vector. So you need to first compute omega cross RB with respect to A, and then pre-cross multiply that by omega. So again, omega was describing the angular velocity. This is a planar motion, so you could say then that because it's a planar motion, my omega is only omega about our third axis, but this is the general equation. So omega, so I have this equation now. So now if you ask me to compute velocity and acceleration of a rigid body, and if I could somehow figure out that this rigid body in fact rotates about a point, this A, if I could identify that A, it would have been really easy, right? Because if I had identified A, I could have computed the translational component of velocities and acceleration, and then add these two components for acceleration and this one component to its velocity. Because once I identify A, I know that I have decomposed the motion into a translational motion and a rotational motion. All right. Thanks for paying attention. And